Hello, guys. We are Group 2, and we're here to present you the report of the first practice related to molecular dynamics. So, first we have to know what molecular dynamics is, and that's a computational simulation method that is used to primarily analyze the motion and interactions inside of a molecular system through time. For that reason, it is necessary to use an HPC or high performance computing that have to be capable of modeling an entire system of millions of particles using the Newton's equations of motion. In this case, we use GROMAX as the HPC. All this to describe the physical chemistry properties of a molecular system, such as entropy, viscosity, solubility, or pressure. Finally, from this, we get a file with the coordinates of the motion of the particles, and that's called a track. Before we go any further, we must know the steps to run a molecular dynamics. First, we have to get a file that models the system, in this case, molecules of water, and for that, we use the model tip3p. Then we have to minimize the system in order to reduce the possible sources of error or non-convergency that are related to the high levels of potential energy that we can get from the running. Then we have to increase the temperature of the system by kinetic energy. And here we start to use the Newton's equations of motion. And that leads us to the first a step that says that we have to let the molecule to propagate the energy. And finally, we have the fifth step um, called production. And here we let the molecules run or move freely in order to get their track. Now we're going to define some concepts that are useful for the completely understanding of the report. First, we have the viscosity, that is a property that we're going to analyze in this report. And it's a thermophysical property of fluids due to the forces of molecular cohesion that result from the fluid's opposition to movement. And this property gives us a brief look into the transport phenomenon of momentum in the system. And we have Newton's equation of motion, that is the foundation of this computational mathematics that we used in the model. And this equation is F equals to the negative of nabla U, U being the force field sensed by the molecules in the system. And this force field is composed by kinetic energy or potential energy, for example. Finally, we have the objective of the practice, and it is to evaluate the effects of temperature in water viscosity using molecular dynamics. Now we can move to the methodology of the practice. During the practice, we followed this procedure. First, we log in to the HPC GROMAX, specifically the cluster of the University Ipatia. Then we get the root to the personal folder using the command pwd when we are inside that folder. Then we copy the folder box1nm into the personal folder using the command cp-r. This folder contains a script that has a code capable of modeling the system of water and inside a box of 1 nanometer that contains around 1016 molecules of water. Then we have to run this script named scriptcalculo.sh with the command sbatch. And this script is going to run three different molecular dynamics related to different temperatures that are 303, 333, and 363 Kelvin, since we're going to analyze the viscosity of the fluid related to the temperature, to the change of temperature. So we can say that inside this step, there are another steps related to the run of the molecular dynamics that we already explained in the introduction. Finally, when we get the results, we downloaded the files that are inside the three folders gotten from the running, each folder related to each temperature that we already mentioned. After the practice, we repeat the same procedure, but using the folder box for an M in this case, that contains a script that runs a box of 4 nanometers of the system of molecules of water that contains around 18,000 molecules. So this gives us a better understanding and a bigger picture of the behavior of the fluid and also more accurate results. However, we couldn't actually run the script because of lack of time, since this takes around 2 days. So we got the results from the professor and continuing with the steps and procedure. First, we selected the tabulator results from the files obtained from the running, and we must know that each file is related to one of the steps that we already explained in the running of molecular dynamics, and we're going to explain them more widely in the next slides. Um, from these results, we used the software MATLAB and plot them in order to represent them in a graphic way using the command or function plot.
Now you're gonna talk about the obtained results. The first phase was the heating phase, and we obtained three scatter plots. First of all, we have the kinetic energy plot, in which we can see that it increased with temperature and time. This is due to that molecules are moving for finding a stable configuration, and there are changes in velocity of the system, and it is proportional to temperature. For the potential energy, we also can see that it increased with temperature and time, and it's a consequence of the movement that molecules are having for finding unstable configuration. And it increased due to the changes in positions that they have, and it also shows that there is less interaction between molecules because they are looking for a stable phase. Finally, we can see the plot for the temperature, and we look at through time, it increased till it arrives to the temperature assigned to each simulation.
Now let's talk about the equilibration phase. Now let's talk about, in general terms, what is the equilibration phase. Basically, the equilibration phase is the phase where the molecules start to move freely in order to distribute the energy equally. The energy that the molecules start to distribute is basically kinetic energy and potential energy. If we compare the heating phase against the calibration phase, we can see that in the heating phase, the graphs start to increase in order to reach the calibration point. But in the other hand, as we saw in these graphs, the potential energy and the kinetic energy trying to stabilize in order to get the calibration point. That's the reason that we can see little fluctuations in the graph. If we analyze this graph that is temperature versus time, basically we can conclude that we have the same behavior as the last two graphs that were potential and kinetical energy. Basically, here happens the same thing. The temperature wants to stay in the calibration point, that in this case are the temperatures that we want to reach, that are 303 Kelvin, 333, and 363 Kelvin.
And now you're gonna show the plots that we obtained for the production phase. First of all, we have the plots for kinetic and potential energy. In both of them, we can see that they have fluctuations through time, but in general, we can see that they have a linear behavior in spite these fluctuations. In the case of kinetic energy, it means that velocity is not significantly changing, and in the case of potential, it's that the position isn't significantly changing. Also, this behavior is due to the collisions between molecules, um, because in this phase we are already in in the simulation of the system. So the molecules are colliding between them, but there isn't like a configuration change. So that's why they have a constant behavior. And now we have the plot for total energy that is in consequence of the behavior that we watched on the first two plots for kinetic and potential energy. It shows a linear behavior, so it is constant through time, and it also is proportional to temperature. We can see that the highest value is for the highest temperature, that in this case is 363 Kelvin degrees.
Now let's talk about the column energy and the van der Waals energy. As we can see in the column energy graph, at lower temperatures, the energy is going to be bigger. This happens because this type of energy depends on the distance. So basically, at lower distance, the energy is going to be bigger. And in bigger distance, the energy is going to be lower. That's the reason why at 303 Kelvin, this energy is bigger. Now let's talk about van der Waals energy. We have something similar here. But in this case, the non-polar extreme of the molecule is the main part of the energy. So basically, at a bigger distance of the polar extreme of the molecule, the energy is going to be lower. And at a smaller distance, it's going to be bigger. That's the reason why at 363 Kelvin, we have lower amounts of this type of energy. Why this happens in 363 basically is because the water is almost near the boiling point. So the molecules are going to be more separate than in 303 Kelvin. Now let's talk about the temperature in the production phase. We can say that we see the same behavior as the pre-production phase. And this happens because the temperature wants to be in the calibration point. The difference between these two phases is that in the calibration phase, we want to stay in the calibration point. Now, in the production phase, we are in the calibration point. So basically, we can now measure the distances in order to obtain the viscosity. Finally, let's talk about the viscosity. Now, as we can see in the table, we have three different values of viscosity for three different values of temperature. We obtain these values from the simulation. Basically, we do an average of all the values that the simulation gave us in order to find like an approximation viscosity for each temperature. Finally, we have the viscosity versus temperature graph. As we see, the graph has a very unique behavior. Basically, it shows us that at bigger temperatures, the viscosity is going to be lower, showing us the dependence of the temperature in the obtention of the viscosity. As a conclusion, firstly, we can say that we show the dependence of the temperature in the viscosity, obtaining that at bigger temperatures, the viscosity is going to be lower. Other thing that we want to add is that these type of dynamics of molecular dynamics are very important in the industry because it helps us to obtain physical, chemical, and biological values that are necessary in the industry, like the Gibbs energy, the entropy, and in this case, the viscosity. Finally, we want to add something important that is the limitants or the problems that have the molecular dynamics that are first of all the time or the amount of period that we take in order to run our dynamic and the area of observation. Basically, in this case, we have a very small area that can obtain us values that are sometimes weird, but at bigger areas of working on the dynamics is going to be more precise and specific. Finally, we have our references. Thank you so much, and I hope that you enjoyed the video.